So the general idea of a pressure swing distillation is just that it's two distillation columns that operate in series. And I'm going to refer to this equilibrium diagram as well. So let's just sketch in some azeotropic equilibrium data. Let's keep the same system from before where P is equal to P1 gives me an azeotrope that has a greater mole fraction than a second pressure, which we haven't really specified. So let's say we have a mixture that is 25% component 1. I'm avoiding using our usual component A because typically we refer to component A as the more volatile. Remember, there is no more volatile component because it switches. So let's just say 0.25 is component 1. Meaning 75% is, of course, the other one. And let's say I have a feed. I'm not going to assume a basis, but I'll assume that the flow rate is known. So if my composition is 25% pure component 1, what are the compositions that I'll be able to get out of the first distillation column? Assuming everything goes perfect, and say we have a ton of stages and we reflux a lot, my limits to what I'm going to be able to get out of this distillation column is going to be nearly pure component 2. So this is why I've written this second axis up here, because I think it's helpful to realize that by specifying what component 1 is, you can also look at what component 2 is. This will be helpful in a second. So when I'm over here, in other words, this is my feed composition, so therefore I'm operating at this, under this magenta curve, right, because that's my P1. I'm going to be able to get down to nearly pure component B, and I know it's component B because my composition of component 1 is 0, corresponding to 100% component 2. At the other end, the best I can do is azeotropic composition. So whatever this is, 65% or so. Let's just say that. Now, of course, I don't want to distill all the way to 65% and 0% because that would be a very tall column with a lot of reflux. So I'm going to relax my specifications just a little bit. I'm going to say that in my first column, I'm going to get nearly pure component B and nearly azeotropic for my other product. And most of the problem solving that we'll do with pressure swing distillation will be determining what stream goes where or where the products are, so to say. So we'll say that the bottom stream, so if you, just look at this, and if I just took this portion of the equilibrium diagram and I zoomed in on that, it kind of looks like something that we're used to, like with the magenta line. So I can go ahead and design this distillation column just taking into account that my XD is going to be approximately azeotropic. So XD is going to be the composition of the distillate product. And for pressure swing distillation, I'm going to do something a little strange and specify it to be a partial condenser. And we don't typically do that, but hopefully the reason why will become clear as we go through today. So this is going to be distillate product 1 slash the feed to column 2. So that'll be a little bit later. We're going to take the distillate product and feed it to the second column. As I said before, this pressure is operating at pressure 1, and we'll say that the composition of this stream is nearly azeotropic for pressure 1. So whatever the azeotrope is for pressure 1, that's what my composition will be from the first column. From the first column, I have a second stream, typical partial reboiler. The bottoms product is going to be nearly pure component 2. Bottoms product 1 and nearly pure component 2. All right, so there's nothing new or interesting about the first column other than I'm limited to what my distillate composition can be. In other words, if I wanted to specify a distillate composition that was greater than 65%, I couldn't do it in this one column. So I'm just going to relax that specification a little bit, and that is going to allow me to design a first column, no problem. All right, so the first distillate product will become the feed to column 2. So I'm going to be careful about where I draw these points now. I'm going to remind you that this is feed 2, right there. This one was feed 1, and this one was bottoms 1. And feed 2 is also distillate 1. So noticing that I am now on the other side of the azeotrope for pressure 2, the idea here is to feed this thing into the second column, except the second column is now going to operate at a different pressure. So P is equal to B2, P2. So this stream, which has a composition, we didn't put a number quite to it. Let's say the number is 60% component 1. That is going to be on the other side of this azeotrope, which is, let's say, 45% pure component 1. All right, so that's going to allow me to, I've now jumped the azeotrope. I'm now in the regime where component 1 is going to be the less volatile thing. And from here, I can design the second column as I typically would do. The only confusing part is that now my equilibrium data is below the line. So how do we treat that? And let's see if I can do this with my tablet. I typically have to draw this up on the board. So let's go ahead and duplicate this. And let's see if I can rotate it. I'm just going to rotate this thing around 180 degrees. And all right, it looks a little bit funky, but not too bad. I'm gonna clean it up just a little bit. Maybe I'll pause and clean it up. Okay, that was a bit of an ordeal. I'm glad I paused it because that was more challenging than it looks, but you guys are worth it. I lost the magenta equilibrium data in the process. I didn't want to draw it back in because it just clutters it. We've gotten from the magenta curve what we needed to from this diagram. So remember that my feed to column 2 is still there. And now we have the same thing. So all I have to do is just rotate the entire curve. And now if I zoom in on just this square, I've got, again, equilibrium data that kind of looks familiar-ish. Right, so here again, I can specify what my distillate from column 2 would be. And my bottoms product from column 2 is going to be nearly pure component 1. And it'll come out the bottoms again. So we got partial reboiler again. And bottoms product 2 is going to be nearly pure, or whatever the specification is, nearly pure component 1. And the tops, I can go back to my typical total condenser here if I want to get my liquid product. This is going to be distillate 2, and this is going to be nearly azeotropic, but it's the azeotrope of P2. And this stream you can typically recycle. You wouldn't want to waste it because there's good chemical in here. You could send it all the way back to the beginning of the process if you wanted to. We won't get that complicated. I think the recycle stream adds another wrench into the problem solving. So we're just going to solve problems like this, assuming that nearly pure azeotrope goes somewhere else after the process. And that's all there is to it. So again, just to recap, there's nothing special to pressure swing distillation. It's just 2 distillation columns. The specifications get a little bit funky because of the azeotrope. And then the only other weird thing is that one of the designs will be upside down because unless you have really good spatial skills, you could always use the same diagram, but then like make your rectifying section operating line kind of like this and step stages like that if you want. So you could do the whole problem upside down if you wanted to. I typically prefer to just rotate my entire paper such that it's similar to what I know. By the way, rotating this 180 degrees doesn't change what the equation for the operating line is. The only thing I'll caution you to say is that you have to be careful about which component you're talking about. So whether or not you use the typical x-axis. So here, when I flip the diagram, my x1 becomes x2. So pay attention to what you've got on your typical x and y axes. And then the only other thing I want to make a note to say is that when you solve these problems, be very wary of solving your material balances. I've learned this firsthand when I specify problems to write them for homeworks. Sometimes I make a specification that is impossible based on the material balances. So just watch out for that. If you're getting something that doesn't make sense, it's possible that it's specified too strictly because there's an extra wrinkle in here of the azeotrope. So sometimes the material balances won't work out. I should show you how to do that. I think I've got a practice problem where that is demonstrated. All right, so that's all for this video. Next time we'll do the practice problem for the day.